Are we rolling? That's going to be in the cut. Okay. I'm not editing this at all. It's just completely raw footage. So, okay. You know, my other class is going to love this, aren't they? Like, we're just... Okay, we're going to roll here. Okay, so we're going to do this integral here. 3x plus 4y squared. Okay, so the idea is, where d is I'm going to fill that in a second. Okay, so D is this region. This is the region we looked at yesterday, one of the regions we looked at yesterday. Okay, that's a 1, that's a 2. Okay, what word should I put here? Do you remember the word for this thing, Skylar?
Annulus.
Yes, annulus, good, you remember. So this is semi-annular region. Okay, so we described this as, well, R runs from 1 to 2, right? Theta runs from 0 to pi. Okay. So this thing is our integration region, D. Now, to remind you how this integration in polar coordinates works, so we had that formula from yesterday, but I would kind of like, don't really go by the formula. Think it through this way. Like, so we really just need to use these conversions. X equals r cosine theta, y equal r sine theta. And what's the other important one?
R squared equals y squared plus x squared.
Yeah, there it is. So x squared plus y squared is r squared. So r squared, x squared plus y squared. So kind of the idea here is, well, let's just take the interval. Everywhere we see x here, this should be dA, sorry about that. Everywhere we see x here, we put in this one. Everywhere we see y here, we put in this one. So we're going to have 3 r cosine theta plus 4 y gets squared, r squared sine squared theta. Right? So all we have to do is substitute in these polar conversion formulas. And now here, like, so dA, well, dA is the polar area element, right? So do you remember what the polar area element is? Yes. Yeah, go ahead.
RDR d theta.
Yeah, there we go. R dr d theta. Now, so just to remind you, so this R, this is not coming from when we're replacing the integrand. This is, we must include this when we integrate in polar coordinates. So this is this factor that gets included essentially via substitution. We have to include this R dr d theta. And now here's how you think about it. Don't use the formula from yesterday. You think about, like, we're integrating over this polar region. Well, my differentials are r and theta, so this is just saying r runs from what to what. Theta runs from what to what. And we can see it from our picture, right? So we can see r is running from 1 to 2. Theta is running from 0 to pi. Okay? And now you just kind of carefully do this out. So let's just bring the r in. 3r squared cosine theta plus 4r cubed sine squared theta dr d theta. Okay, now I actually am going to carry out the integration here. So let's do I1. How's it, you getting a good angle from over there? Is
Yeah,
this
it's
gonna
fine,
work?
it's
Okay,
fine.
good. Okay, so I1 here, so we're gonna go from 1 to 2. And we're just integrating this one with respect to R. Okay, let's go for it. This one with respect to R, what do we get?
R cubed cosine theta,
Yeah, R cubed cosine theta.
or not, oh yeah, yeah.
Yeah, R cubed, yeah. And the other one?
R fourth sine squared.
Yep, R to the 4th sine squared theta. Okay, and we're going from 1 to 2. Okay. So let's just carry this out carefully now. So we're gonna get 2 cubed is 8. 2 to the 4 is 16. Just doing our fundamentals here now. Minus 1 cosine theta. Minus 1 sine squared theta. Okay, clean this up. 8 minus 1, 7 cosine theta. 16 minus 1, 15 sine squared. Alright. Okay, so this is just our inner integral. So our outer integral, we're running from 0 to pi of, let's see, grab that one again. Okay, we're going to be integrating this now, 7 cosine theta plus 15 sine squared theta. So this is why I want to do this integral out. The sine square integral has appeared. Okay, so this thing will be appearing many, many times throughout the rest of the course, either the sine square integral or the cosine square integral. So I want to remind you guys how to do this. So well, let's just go ahead here. Now, let's do this up the long way, but I just want to make some commentary here. Like, just think about, via geometry, what's the integral of cosine from 0 to pi? It's 0, right? So you can start, like, once you see a lot of these, you kind of develop an intuition for which of these are going to be 0. But let's just do it out in full. So we're going to get here, well, before I do anything to this 7 cosine, let's just keep that there. This sine square. Do you remember how we handle, that is a nice marker. Do you remember how we handle the integration of sine squared, Dylan?
1 minus cosine squared.
Uh-huh. Well, okay. Yes, but then we're gonna have cosine square, right?
So then u equals cosine.
Oh, well, but then we would have a du as sine.
Wait,
Okay, let me take Sam.
This has got you kind of ordered when you do the reduction,
Oh, okay. We could do a reduction formula here. Now that arises from integration by parts of this thing. Okay, that would work, but there's an easier way. Yeah, go ahead. There it is, the half angle. You know, only a math major. Right? So we use the half angle formula here. Now, what is the half angle formula? Do you remember it? There's a 1/2. Yep.
Something minus 1/2. 1/2 times 1 minus.
There you go. 1 minus.
Cosine 2 theta.
Bingo.
Yeah.
Good.
Okay.
There it is. So this is the half angle identity. Half angle formula. For sine square, 1 minus cosine 2 theta over 2. What's the half angle formula for cosine square? Plus, right? We just got a plus here instead of minus. Okay? So let's just carry this out now. So this is going to be, so just be careful now. Okay? Why don't I just make this a 15 over 2? is to, so we're gonna get a 15 over 2, 1 minus cosine 2 theta. So here we're gonna get 15 over 2 minus 15 over 2 cosine 2 theta, d theta. Okay. Now, just for the sake of our time, it's, well, I think most of you are comfortable with integrating this where we are now, right? So we're just, integrate cosine, sine, integrate a constant. Now this one, I mean, you can do it in your head if you want. If you're uncomfortable with that, you just do a u sub with u equal 2 theta and you can make it there. Or you can just be smart and say, well, like we said, this integral is going to be 0. This integral is also going to be 0. So at the end of the day, we're just going to be integrating this constant 15 over 2. What's the integral of a constant over an interval?
The constant times the interval?
Yeah, the constant times the length of the interval, right? So we're just going to get 15 over 2 pi at the end of the day. So, if you're uncomfortable with that, go through this at home. You can definitely integrate all this, do the fundamental theorem. This will come out. Okay. So let's have a look at another one then. What a mess. Okay. So this one. Okay, we're looking for the volume of this solid bounded by the xy plane. And this paraboloid, z equal 1 minus x squared minus y squared. Okay. So this is, now that previous example is kind of, well, we were given some region which is obviously described in polar coordinates, so it's clear to use polar coordinates. Now this example, you're going to see really why this transformation to polar coordinates is helpful. So let's just go ahead and it's good practice on these to just sketch them. Okay. Now there is a way to see this algebraically too, but to me the sketch tells us all. So, okay. Okay, now, well, so this is where, once we go through this part of the course, remember how I always ask you guys, like, what surface is this? What does this surface look like? Like, once we go through this part of the course, if we went back in time, this is where we get really good at identifying surfaces and graphing them and stuff. So like this paraboloid. So this is well, it's actually a circular paraboloid. Now how do we graph it? Well, this minus stuff tells us it's pointing what way? Down, right? Now this, what do you think the 1 does to it? Well, it's going to move it up 1, but yeah. So just like how this works for a regular parabola in xy plane, shifts it up 1, we have the paraboloid pointing down. So what this will look like is, well, this isn't going to be to scale, but if I put 1, basically we're going to have a 1 there. Paraboloid pointing down. Okay, so just kind of think about this for a second. essentially what's going on is, if we look at the traces that are just in the ZX plane, let's look at that one. That means set y to 0. You see we have this parabola z equal 1 minus x squared. Now we know what that looks like. I've gone up 1. I'm just going to be this parabola pointing down. Where am I going to intersect the x-axis? 1, right? And minus 1. So I'm going to get kind of this thing. Okay, so this is just my trace in the xz plane. What is my trace going to be in the yz plane? Well, that means x is 0. We're just going to have the parabola 1 minus y squared. Okay, this is just a parabola in the zy plane, shifted up 1, intersects the y-axis at plus or minus 1. There we go. You guys see it? So now check this out. What do we have here? We have a circle. We have a circle. Okay. Now let me just label these. This is 1 and 1. So you see what's going on here? We want the volume beneath the paraboloid and above this circle. Well, we're talking about this double integral. Z is 1 minus x squared minus y squared. Where D, well, what circle is this? It's the unit circle. How can we describe the unit circle in polar? 0 to 1, right? 0 to 1, right? The radius of this thing is 1. 0 to 2 pi, right? We're going around the whole circle. Okay. Now, how do you get this without the sketch? Well, intersect this surface with the plane z equals 0. Put a 0 in here. Right? Rearrange this thing. X squared plus y squared equals 1. Unit circle. Okay. So a lot of the times we have to do a little work to figure out, like, well, what actually is this region D, and how do we express D in polar? Go ahead.
So why would we draw the graph? That seems like a lot faster.
Yeah. So this was a lot faster, but okay, good question. Like sometimes it won't be as see this surface is fairly straightforward, and this is fairly straightforward. Sometimes it won't be like if you have like an offset circle or something like that, or yeah. So it's a good habit to get in the habit of sketching these things. So now let's do our polar conversion here. Right, convert to polar. Okay. Well, what is 1 minus x squared minus y squared in polar?
R sine squared theta minus r squared sine squared theta.
Mm-hmm. Yep. So that's correct, but like we can do a little faster, right? Because 1 minus r squared, right? Now, how are we seeing that? This is because right? And in polar, x squared plus y squared is r squared. Okay, so this is going to be 1 minus r squared. Now, what is our polar area element? R. And our differentials? Yep, drd theta. R runs from, yep, theta runs from, yep. So that's our setup. Okay, that's our setup. So Now this integral, well, this is just gonna be some polynomial in R. You're gonna be integrating R minus R cubed. So the integration here should be fairly straightforward. I know that you can all carry that out, so for the sake of time, I'll just, we don't have to go through it. You actually get pi over 2. Okay, so kind of the purpose of this exercise is showing you that, well, sometimes we have to sketch the thing or do some other algebraic argument to determine that, yes, we really are going to integrate in polar coordinates. Okay? Now this is kind of cool. Like imagine if you just like took another one of these and put it on the bottom, the volume is pi. It's always nice when things come out to pi, isn't it? So, okay. So let's have a look. This should be good timing. So I think we can do one more here. Okay, so let's see. New example. Find the volume. Okay, so we're under the surface z equal x squared plus y squared. Okay, so now we're going to play our game again. This surface is, oh, okay, sorry. So not in polar. So more like this surface is a what? Cylinder. Well, sphere. Well, keep going. I think I heard it. Do you say it, Caleb? Oh, elliptic paraboloid. Yeah. Wait, what did somebody say it is? It's a Taylor series? Well, I guess, yeah. Okay. So this surface z equal x squared plus, this is a paraboloid, right? So it looks kind of like this one. Now, yeah, it's an elliptic paraboloid. It's really circular paraboloid. Circle is a special case of the ellipse. So we're above this, we're under this paraboloid, and we're going to be above this disk. All right. Okay, so sketch. This one let's have a sketch. Whatever that says. Okay. Okay, here we go. I think before we make our 3D sketch, we should probably, I'm on film, I gotta pull out the pointer at least once. We should probably talk about what that is, right? Well, it's a disk. We actually talked about this one yesterday. Do you remember what it is? Yeah, Johan?
The circle that intersects, it's like 2 cosine. The circle that intersects like on the left side of the x-axis.
Yeah.
Y-axis.
Yeah, so it's kind of this offset circle, right? This one. Right, it has radius 1, but the center is at 1, 0. So this is the circle, so we're not going to really, just for time, so we talked about this yesterday. This is in the start of the notes on polar coordinates. This circle can be expressed as, well, I think somebody said it. It has the polar equation, what? R equals 2 cosine theta, right? So 2 cosine theta. Okay? So let's just get this out of the way now. Like if we want to talk, so we're integrating over this whole region. So just to kind of, we talked about this yesterday, but just to refresh you, if we want to describe this in polar, we put what bounds on R. So yeah, 0 up to this function, right? Up to 2 cosine theta. Now how about on theta? See, this one's a little, I think you guys will get this. Dylan?
Is it pi over 2 or negative pi over 2 to pi over 2?
Yeah, that'll do it. Negative pi over 2 to pi over 2. Yep. Right, we're just going from minus pi over 2, pi over 2, we capture the whole circle. Okay. So let me kind of get the sketch here. Like, from here, you could probably set this up without sketching it in 3D. But let's just kind of get this. Okay, so this, just make sure you put it in the right place, like this. Okay, we're in the XY plane here. So this circle is really like right there. Now, and what is the, so we're under this surface, z equal x squared plus y squared. Okay, so what does that one look like?
Like that one, but just pointing up.
Yeah, it's this, but pointing up, right? So the vertex is going to be here at the origin, pointing up. So this is, for me, this one is kind of hard to draw, but let's see how it goes. So we kind of have this paraboloid, or parabola, and this parabola or something. Traces are these circles on the z-axis. Now it's kind of hard to picture what happens here, but it's like this thing comes up. So we almost get this cylindrical shape, but this one side of it is bounded by this paraboloid here. So maybe if I get my red pen. Kind of like the boundary of this face it's actually going to be an ellipse. But anyway, can you guys kind of picture it? Yeah. So let's go ahead and do the, let's go ahead and set this integral up. Okay? So what are we doing here? Well, let's start like this. So we're find the integral over d. So d is this. Our surface is x squared plus y squared. Okay. So let's go through with it. So somebody said this when I think Matt said this, x squared plus y squared is r squared, right? What's my polar area element? Yeah, there we go. RD theta goes here. Okay. So, let's not write another line. Let's just agree r squared times r is r cubed, right?
Yep.
So let's just go ahead. Yep. Let's just go ahead and write r cubed here. Okay. Now, it's nice that we take care of our work as we go. We already determined our bounds on r and theta. Right, so again, what's going on here? We're talking about the integration region D. We're talking about the bounds on r and theta to describe D. R runs from 0 to 2 cosine theta. Theta runs from minus pi over 2 to pi over 2. There we go. This is our setup. Now, we're going to do the integration out here. Carefully, very carefully. So our inner integral. Okay. Well, this is no problem. What's the antiderivative of r cubed? R to the 4 over 4. you see how this is gonna get ugly? We have to put this to the fourth power. What's 2 to the 4?
16.
Yeah, what's cosine to the 4? Cosine to the 4. What's 16 over 4? Yeah. There. Okay, so the inner integral, fine. Then we have to do this outer integral. For cosine to the 4 d theta. Okay, so let's go for it. We're gonna need this whole side of the board here, I think. Okay, what do you guys think here? Organic chemistry tutor ain't got nothing on me when this hits YouTube, right? So, let's see. We're integrating this thing, right? So. Okay, here we go. How should we handle this? So, okay, reduction formula might be nice here, but let's forget about the reduction formula. Okay, what should we do here? Go ahead.
Can you break it up into 2 like cosine squared thetas and then use
Yeah.
the identity we were using on the previous example?
Yeah, that's the idea. So we have to break this into cosine square, square. Yep. So what we're gonna do, why don't we take the 4 out, just so we don't get too cluttered here. This cosine to the 4 is cosine square, square. Okay. So let's do it like this. Cosine square, well, I erased it, but maybe you remembered. We're going to use the half angle formula here to open up the cosine square. What's the half angle formula for cosine square?
1 plus sine 2 theta divided by 2.
Yep, so except we're going to have cosine here.
Oh, yeah.
Yep, so 1 plus cosine 2 theta divided by 2. So that's cosine square, but we're squaring it. D theta. Okay, so let's just go through this, be really careful here. Well, the first thing I'm gonna do is I'm gonna say this, and I'm not really gonna write it. When we square the 2, we're gonna have 1/4, right? 1/4 is gonna hit that 4, gone. So really what we're going to end up with here is 1 plus cosine 2 theta squared, right? That 1/2 squared and that 4 just take care of each other. Okay, so let's square that thing out. One. Okay, I'm just squaring that out. Plus 2 cosine 2 theta plus cosine square 2 theta. Agreed? Okay. Well, now what do we have to do? This thing? We have to do the half angle again. Okay? But see, you have to be really careful here. So let's just go ahead. 1 plus 2 cosine 2 theta plus, okay, here we go. Half angle says, well, 1/2. 1 plus cosine, here's where you be really careful. What do I put here?
4 theta.
Good, good, good. 4 theta, right? So the half angle, whatever the angle is here, right? So when it was theta, you double it. 2 theta, so where is it? 2 theta, double it, that's a 4 theta. Okay? D theta. So let's just, carefully go through this. I'll put my integration limits back in, minus pi over 2 to pi over 2. 1 plus 2 cosine 2 theta plus 1/2 plus 1/2 cosine 4 theta. D theta. Now this is, let's just kind of collect here. 1 plus 1/2, this is some number, right? 3/2. Plus 2 cosine 2 theta. Plus 1/2 cosine 4 theta. Okay? Okay. So, okay. 2 questions. From here, I mean, kind of rhetorical, like you can just think to yourself, can you integrate this from here?
Yeah.
Yeah, right? Like this is integral of a constant. This is just going to be some u sub. Do it in your head if you want. Okay. Well, here's the other question. If you had to integrate 4 cosine to the 4th on an exam, like a midterm that's coming up in a week, do you think you could do it? With the cheat sheet, sure. Like if you practice this integral, do you think you could do it? What if I put a sine to the 4? Do you think you could do it?
Just one minus cosine.
Yeah, we would just have a minus here, right? So this is going to be on the record, right? This is on film now that I've said this, and there's a midterm coming up. Okay. Now, sure, you could integrate all this, but we can be a little smart here. What do you think this integral is? Or what can you logic through this integral is on that interval? 0. What about that one? 0. So we have the integral of a constant. What is the integral of a constant over some interval?
3 pi over 2.
There it is. So it's the constant times the length of the interval. The constant is 3 pi over 2. Is 3 over 2. The length of the interval is pi. There we go. So that's it. You can cut the film.